Good morning and welcome everyone. I'm Silvia Romagnoli, full professor of applied math at University of Bologna, and I'm going to deliver a lecture about the simulation approach to evaluate the value at risk. Let me share my screen. Okay. You should see my slides. Okay, here are the table of contents. So after a brief introduction of the simulation approaches, I'll go on detailing both the historic simulation and the Monte Carlo simulation, providing also a comparison of the two methods. Finally, we discuss the quality level of our approach, thanks to the backtesting argument. Okay, so the aim of this lecture is to focus on the simulation methods as a proposal to overcome the drawback of the parametric approach. We analyze both historic and Monte Carlo simulation, discussing pros and cons of the two methods. Finally, we'll talk about backtesting to check if we can trust the evaluation of value at risk we have done. Well, the main features of the simulation approach are, first of all, a huge number of scenarios concerning the future evaluation of return, which must be generated. This means that we refer here to a full evaluation of the value at risk versus a reduced evaluation, as in the case of the parametric value at risk, where all possible movements, future movements of the returns are represented by the calibration of the standard deviation. Therefore, the simulation methods are more intensive from a computational point of view, but also more accurate and flexible because we don't have any constraints concerning the normal distribution of returns. As a matter of fact, the quantile logic is here applied on an empiric distribution of returns instead of the normal one. The main assumption of the historic simulation is that the future dynamics of the returns of a portfolio or of an asset are well described by their empirical distribution, meaning that the past is a good forecaster of what will happen in the future. We can say that the stationary assumption of the returns distribution must hold true. The key factors of the historic simulation are, first of all, the computation of the returns recorded in the last T days, which can be, for example, represented by 250 days, and obviously their empiric distribution. We need also to identify the quantile at a given confidence level of this empiric distribution. Therefore, given a confidence level, which is, for example, equal to 95%, the historic value at risk is the 1% quantile of the empirical distribution of the returns, which means we are confident at 99% that the returns won't be worse than the value at risk. Obviously, if we refer to daily returns, we know that our forecast refers to the day after. Okay. As we did for the parametric value at risk, well, in this case, we omit the negative sign and represent the value at risk as a positive number. In the picture, we can appreciate the histogram of the returns recorded by AIG in the last 250 days. On this empiric distribution, so we highlighted the value at risk at 99% and 95%, which are the quantiles at 1% and 5% respectively. Let us discuss the advantages of the historic simulation approach. So first of all, we can observe that it is very easy to be implemented and understood. Moreover, there's no a priori hypothesis about the returns distribution. And we generate an estimation of the value at risk, which is stable in time. This is because the value at risk won't change until we record a return worse than the critical quantile. On the other hand, we have some drawbacks. So first of all, this method is based on the assumption of stationary returns distribution, which is not always supported by empirics. Moreover, it might request an intensive computation due to the full evaluation feature. And moreover, when the time series is limited in length and we evaluate the value at risk for a month, for example, or a year, we could have a misspecification of the tail of the value at risk. As a matter of fact, there is a trade-off in the definition of the estimation window, because if we consider only the most recent data, we could have not enough data for the estimation of the value at risk. On the other hand, very old data could falsify the information due to incoherency with the current structure of the market. The second simulation approach is the Monte Carlo method, which is based on the generation of random data given a probability distribution which fits real data. The method works as follows. So given a set of real data, we choose a distribution and estimate its parameters. It is a parametric method, so therefore we must choose a distribution based on goodness of fit argument, as for example, it might be the normal or the t-students distribution among the elliptical family. As a second step, given the calibrated distribution, we sample capital N returns from this probability distribution. So we can observe that it is possible to increase the dimension of the real sample data. Moreover, if capital N is high enough, we end up with a not distorted estimation of the value at risk, which corresponds to the mean of the simulated values. Well, this procedure sounds as follows. So first of all, we need to select a probability distribution, which can be a normal one, a student t, etc. We need to calibrate it on the market data. We note as P the cumulative distribution function at level Q, where Q stands for the quantile of the probability level P. We carry on and we evaluate every quantile Q corresponding to every P. These obviously are the simulated returns. Then finally, we evaluate the quantile such that at a given confidence level, it represents the value at risk. In the picture, we have a T students probability distribution with 2 degrees of freedom, which is the selected distribution of returns. We can observe that for P equals 0.3, which is represented by the red area, we have a quantile Q equal to minus 0.617. Take in mind that this method requests to simulate at least 1 million returns. We consider the following empirical example based on the returns of JP Morgan from the data set of its prices. We proceed assuming that normal distribution is coherent with the data set and estimate the mean and the standard deviation of the JP Morgan returns, which turns out to be sigma equals 0.04055913 and a mean equal minus 0.0008030195. Then we proceed generating 1 million random variable of P, and then we recover the corresponding quantiles of the calibrated normal distribution. Finally, the value at risk at the confidence level 95% is the quantile at 5%, as you can see in the picture below, and it corresponds to a value at risk equal to minus 0.0673606. We can list the following pros and cons of the Monte Carlo simulation. So first of all, it is based as a full evaluation. This is a good thing. As you can fully reproduce the returns dynamic. This obviously as in the historic simulation approach, as we mentioned before. Moreover, we can choose every kind of probability distribution, so we don't have any constraints concerning the normal distribution one, as we have in the parametric approach. But as a cons, we must say that well, a probability distribution must be chosen in order to simulate the returns. So an assumption must be done concerning the distribution of returns. And well, this method is heavy from a computational point of view. Well, the last topic we are going to approach refers to the evaluation of the quality of the estimation of the value at risk. This is a very important argument for the regulatory authorities, as stressed in Basilea agreements. As we have our estimate, we aim to know what is its forecast power. So in order to give a first evaluation, we must compare the effective realized return in t+1 with the estimate value at risk at the previous period t. So we must do this comparison obviously ex post. And for this reason, we talk about back testing. So we can say that the backtesting procedure is based on an ex post analysis where we compare the realized observation to the forecast of the previous period. Var T1 minus T, the estimate of the value at risk at time t with probability 1 minus C, where C stands for the confidence level. So as for example, if the confidence level is 95%, we have 1 minus C is equal 5%. So we compare this estimated VAR with the realized return at time t plus 1. Therefore, the comparison is done at time t plus 1 when the return is well known. We define then a binary variable. We note this binary variable as x at time t plus 1. This variable is said to be equal an indicator function on a set which represents the returns lower than the VAR threshold. On this set, we have a violation, meaning that if this is the case, at time t plus 1, we had a loss greater than the forecast of the value at time t. That is to say, the value at risk in this case failed in its purpose. We repeat by estimating the value at risk at time t plus 1 and comparing it with the realized return at time t plus 2. The rollover produces a number m, capital M, greater enough of binary values. This way, we are able to evaluate the number of violations, which is defined as x cap, which is the mean of the binary random variable. Finally, we compare x cap and 1 minus C. Nearer they are, either the forecasting quality of the value at risk, because 1 minus C stands for the left tail of the returns lower than the value at risk, as exactly the violation are. If the violations overlap 1 minus C, it means that the confidence declared by the value at risk estimate has been respected by the empirical ex post evidence. Let's see an empirical example. We consider the daily returns of Morgan Stanley and we implement a backtest. So we iterate a rolling procedure with the chosen estimate window. Here we choose t equal 100 days. And then we estimate the VAR through the historical simulation, assuming to have a confidence level equal to 95% and taking into account the daily returns. Then we compare this value at risk to the returns recorded at time t plus 1. And we define the binary variable, which in this case is null. So we don't have any violation because the realized return is greater than the estimated VAR. At day t equal 101, so the day after, based on the past 100 observation, we estimate a new value at risk and we compare it to the realized returns at time 102. Also, in this case, we have a null binary variable because the realized returns is always greater than the estimated var. Given our data set, which is composed by 4,002 returns and a window of 100 days, we can have capital T minus T, that's 3,902 estimates of var, in order to use all the available information. The picture represents the estimated value at risk in time based on the historical simulation. In this picture, we compare the evaluation of the value at risk with the realized returns from T plus 1, which is equal 101, to capital T equal to 4,002. We can graphically appreciate the violation whose mean is equal 0.0604818. We can observe that the violation correspond to extreme events, as in this case here, that's the subprime events. To accept the null hypothesis of good performance of the model used to estimate the value at risk, we have several performance tests. Among them, we have the unconditional coverage test proposed by Kupiec in 1995. In this case, we have a statistical test based on the distance of 1 minus p and x cap. That's the number of violation. This distance is distributed as a chi-squared with 1 degree of freedom distribution. The null hypothesis of good performance sounds as 1 minus p equal x cap. Also, in this case, we must assume a confidence level, as for example, 95%. Take in mind that this kind of test does not consider correlation in time of the violation. On the other hand, the unconditional coverage test proposed by Christofsen in 1998 extends the previous one, considering also time correlation of violation. We implement the test in our empirical example, considering an annual window, so we consider a window composed by 250 values and estimate. And we implemented the test considering a confidence level equal to 95%. In this case, we have, in our example, we have expected exceeds, which is the 5% of 2050, or 12, because we consider also a confidence level of 95% also for the estimation of the value at risk. We have actual exceeds equal to 14, therefore the distance turns out to be equal to. Now we know that the distribution of the statistic is chi-squared and the confidence level of the test is 95%, so 1 minus c is results to be equal 5%. Therefore, we recover the quantiles of this distribution at 5%. This way, we recover the statistic test for the Kupiec version equal to 5.99, while for the Christofsen version equal to 3.84. Both these tests fail to reject the null hypothesis. Because the statistics are both greater than 2. which is the distance, the recorded distance. We can conclude that the historic simulation approach provides a good forecast on the first year at least. Here you have a useful suggestion for further reading, and thank you very much for your attention.